Good evening, all. We have an arithmetic progression here with a common difference of 9. We want to show that this arithmetic progression, I'm calling it S, has an infinite number of terms with the same prime divisors. Now, just to be clear, make sure I'm making sense on that, let's say 24, 72, and maybe jump up to 144. Now notice these are different looking numbers, right? One of them's 3 digits, in fact. But you'll note, and I won't go through the work here, but the only prime divisors of all 3 of these numbers is 2 and 3. Okay, now that's maybe is unbelievable, but this is 12 squared, and 12 is just comprised of 2 and 3. So if you square that, you still, or it's these 3 terms have the same exact prime divisors, namely 2 and 3. So that's what I'm trying to get across right here. It turns out the structure of an arithmetic progression, arithmetic sequence, allows us to prove that there's an infinite number of terms in this progression with the same prime divisors. Okay. Now let's move along here, and this sequence S is literally defined by this congruence. Okay, the positive terms is what I'm interested in. So any y that is congruent to 4 mod 9 will be a member or a term in this sequence. For example, 31 minus 4 is 27, which is divisible by 3. 22 minus 4 is what? 18, which is divisible by 9. Now, what did I say a while ago? 9. But anyway, 40 minus 4 is 36, which is divisible by 9. And every single term in this arithmetic progression is defined by this. Now, another way of writing this, which some people prefer, is you can replace the congruence with equality, good old-fashioned equality, and just write down 4 plus 9k. Okay, a lot of people don't trust congruence. I did for the longest time, but now I love it. You know, I really think it's fascinating stuff. Now, and let's see, what do we need here for our k? Our constraints on k would be k is greater than or equal to 0, an integer, right? K greater than or equal to 0. And literally, if you just start moving with all the integers greater than or equal to 0, you spit out this arithmetic progression. Okay, now let's proceed. Now, y'all, another important fact here, which wasn't obvious to me until I did some exploration on this, is this idea of a multiplicative inverse. Notice that 4 times 7, and this is, I'm not really disclosing all the discovery I did here to notice this, but so I'm just writing it down, which is sort of a lack of motivation here. But this is congruent to 1. Mod 29 up here, mod 9, excuse me, okay? Again, 28 minus 1 is 27, which is a multiple of 9, okay? That makes 7 what they call the multiplicative inverse, because you're getting 4 times 7 is equal to 1 in some sense, modulo 9. You know, just like 1/3 times 3 is equal to 1, or that's how reciprocal is defined, or reciprocal times the number is going to be 1. It's the same thing here, except we're dealing in modular arithmetic. Now, that turns out to give us a quite easy way to prove things here. If we define a term, and this is, think of this as a function of n, okay, we take the first 2 terms of our sequence, which is 4 and, we take the first term plus the common difference, right? Now, you see how I write the 4 times 7 raised to the n power right here? Remember, 4 times 7 is congruent to 1. So I just showed you right up here. Okay? So you see how this is, it looks kind of like what, you know, but then you go, well, and also 9 is congruent to 0, of course. That's trivial. I hate to use that word, but I can't think of a better word. 9 is congruent to 0 mod 9. For the simple fact that 9 minus 0 is 9. Okay, so 9 is congruent to 0 modulo 9. It's useful to think of that when you're doing Wilson's theorem and other things. And so we get this, and I'm writing this out for emphasis, right? Okay, I'm writing this out for emphasis. I could have skipped this step, but what we get is a sub n, and I'll write this. Just all of this line amounts to is that a sub n is congruent to 4. Right? But you see, that's exactly how we defined our arithmetic progression. Y congruent to 4 mod 9 when we have a to the n is congruent to 4. So that means an is a term in the sequence. Some people might want to write it as a sub n is a member of S. Okay, if you want to think of it as a set. Okay. Now, so isn't that cool? Because you see what we have right here, folks, and let's write this out. We have a sub n as a number is equal to 13 times 28 raised to the n power. And it's a member of our sequence, right? But what are the prime divisors right here, folks? Well, 13 is prominent, 2 and 7. So you see, folks, we have defined an infinite subsequence that has only these values as prime divisors, 13, 2, and 7. So we're already QED time. Now, I thought it was kind of neat little idea that takes advantage of the notion of a multiplicative inverse, okay? Now, I've written down a few of these for you if you want to. We're done with the proof, but to breathe a little more life into this thing, let's do n equals 1. For n equals 1, y'all, the computation, and I've double-checked these, so I'm pretty sure I'm right. N equals 1 implies a sub n, and it's understood that we're talking about a sub n here. A sub n is 364. Right, folks, I'm just saving a little bit of work here. That means a sub n is equal to 364. That would be 13 times 28 because n is 1, right? Now for n equals 2, and again, I won't bore you with the arithmetic here, but for n equals 2, we get a 5-digit number. Okay, we get a 5-digit number. What I got here is 10,192. It's hard to believe in a way, isn't it, folks? But all of these numbers just have these are the only prime divisors of any term in the sequence, simply because it's manifestly defined this way, where 13 is constant, right? And then you're just stuck with 28, which is 2 squared times 7, right? And let's just do one more if you want. N sub 3, for n equals 3, I ended up with good God, 285,376. There's probably some other problems you can do with all of this now that we've created this sequence. It's kind of a strange looking object, but it in and of itself, maybe it could be the stuff or the origin of other types of problems, But anyway, all of these numbers, without checking, unless you just don't trust me that I calculate them correctly, these numbers and all the other ones as n grows would be terms that contain only these 3 prime divisors, 2, 7, and 13. So again, the proof, we were done exactly when we wrote this down. These are just some examples. And so, folks, that's it. And I thought that was a cool problem. I think Polya was interested in this kind of stuff and maybe came up with the first proof of something like this. And y'all, what's fascinating, if you just look at the number, like say 49 is the next term, right? See, this would be 7 squared. This would have 5s and 2s. This is a prime. This would have 2 and 11. So you see, there's no indication that that something like this could be even possible, because just, of course, the first 5 terms, 6 terms, but the next one would be what, 58? So that would give us 2 times 29, right? But still, we don't have anything close to proving, there's nothing about this initially that would make you think something like this could possibly be true. Okay, that's the difference between the finite and the infinite, And you can go out a lot further and there would be nothing that would convince you that something remarkable like this is true. And moreover, it's 3 distinct prime divisors. Now, it helped a little bit that 9 plus 4 turned out to be a prime. If 9 plus 4 wasn't a prime, it would have prime divisors, and this list would be longer. But anyway, I'd like to know what you think. I think it's a cool problem. I like this kind of stuff. Thank you for viewing.